All right, good afternoon, everybody. My name is Adrian, and I lead our platform architecture team here at Microsoft. So today I want to talk to you about Mt Diablo and why and how we're using power disaggregation to power the next wave of our AI systems. But before we get to the next wave, let's actually talk about what does an AI rack look like, what's inside of it, and what's motivating some of these changes. So if you look at the four core ingredients, you have the AI accelerators, that's what we know and love. We've got the scale-up switches. Those two pieces kind of form the backbone of the AI system. But we also have our power conversion, we have our management fabrics, our front-end fabrics, how we actually talk to other systems across the Azure infrastructure. And those are in relative kind of size and scale of what it looks like inside of a rack. But if we actually want to go bigger, we want to put more accelerators in our rack, if we want to make things more efficient, a few things stand out. It's only about 60-ish% of the rack that's AI accelerators and those scale-up switches. It's not a lot. So what would we want to do if we want to put more accelerators, go to higher power accelerators, and give us some of that flexibility? Well, it's kind of the obvious answer is, let's get power out of there. Power continues to scale both on the accelerators as well as the AC to DC conversion side. You add a little more accelerator, you need more power conversion. If you pull it outside of that critical stack, now you end up with 80–85% or more of the rack that you can use for the AI accelerators. This gets you to bigger pod sizes, allows some more efficiencies, and I'll talk about a few more pieces of that in just a moment. So that kind of changes what an AI system looks like, right? Today, we roll in a rack, and it is the AI system. It has all those ingredients I showed you earlier. It just rolls in, plug it in, and we're off to the races. Now we're actually going to start splitting those into two pieces. One that's focused on the core competency of AC to DC power conversion, and the other that is the server rack, AI rack, that puts all of your IT equipment in there. And so why do we want to do this? So let's actually talk about this disaggregated power conversion rack. So it looks like a standard rack, and we can scale up and down the amount of power and even the topologies we want to support in there. So what if it's a 50 kilowatt rack that you need to support, 100 kilowatt, 300, 500 kilowatts? You kind of see the theme. We're going higher, we want some flexibility. But it also gives you the opportunity to right size and kind of dial in what do we need and what do you need for your infrastructure. Whether that's feed redundancy, what's important to you, power shelf redundancy, do you want to have an extra power shelf or two? Power supply redundancy, do you want an extra power supply in each shelf? Do you want to have some number in the entire rack? It gives you the ability to dial it in just the right way. And what's kind of interesting about this, we can start with today's 48-volt architecture. We can start there while we start building these higher voltage DC, 400-volt systems that I'm going to talk about in just a moment. And the other kind of interesting part here, when we put more things into a rack, whether it's AI accelerators, you have all these cables going in and out. Well, people often forget what's going around the backside of that rack. So here's an example just showing a bunch of AC whips. That's messy, that takes up space. When you are not 100% liquid cooled, you need airflow that's going back and forth through there. You already have manifolds and bus bars. You also have these AC whips to contend with. So it's really nice when you kind of pull that out of the critical stack and you allow kind of the left-hand side here to focus on power conversion, getting AC in, and then the AI side actually doing the AI processing. Which brings us full circle to the slide we showed at our keynote the other day. Couple exciting things here. So we're going to be talking about 400-volt power conversion. We also want to make sure this scales. It's not a one-time solution. It's going to scale to the portfolio, and it is accelerator and basically server agnostic when we do this. We no longer have a tight coupling. And what's really cool is we're actually going to contribute the spec on parts of what we're doing here. With Meta. It's an excellent opportunity for collaboration, and you'll see that theme at the end. I'm going to encourage everyone to come join us for this. This makes sense. The parts are here. We want to keep going. But now let's actually talk about the 400 volt. Right now, we've really talked about the value of disaggregating. But let's get into the 400 volts. So let's take a hypothetical. Let's say it's a 500 kilowatt rack that you need to support. What would a bus bar look like in a 500 kilowatt rack? You do some basic math. 56 millimeter diameter, that is a massive piece of copper, and then it's going to span the entire rack. That's a lot of copper. Are there other ways? And yes, there are. So what if we then extrapolate that to 400 volt DC? That 56, drops to around 20 millimeters. That's a bit more reasonable. But if you do plus minus 400 to give you an effect of 800 volts, that drops further to a diameter of 14 millimeters, a lot less copper. So let's put this into perspective. I know it's always hard to think of a measurement in the abstract, but 14 millimeters, that's a AA battery. You know what a AA battery is? That's small. Imagine that going the whole rack. Not that bad. So 3 kilograms, 6.5 pounds. That's actually pretty reasonable. Not a lot of copper. Take that 56 millimeter, the top of a Coke can. That's pretty big. So you scale that up to a 2-meter rack. Now you're at over 100 pounds or 47 kilograms. That's heavy. That's a lot of copper. So when we talk about sustainability, reducing the amount of things that we need to put into our racks, here's a pretty obvious one to reduce our reliance on some of the copper. So high voltage DC in particular, it's not new. It's been done. The car industry is already moving to 800 volts. You see a lot of EVs already using that platform, so it's pretty efficient. That means there's a lot of other downstream components that we need, whether it's the conversion technology and other components that are rated for these types of voltages. So we have that as an ecosystem. Now let's actually bring that into the data center and use it for our needs as well. And here's kind of the call to action, right? We're kind of showing the idea. We will have a contribution coming out pretty soon where we will contribute the specifications of the Mt Diablo rack. What does a disaggregated power rack look like? What components are inside of it? How we can start driving commonality? And it's also up for your interpretation as well. If you noticed in the renders earlier, the whole rack is not completely full. If you have other needs for power stability and conversion, you have space. So you can kind of take some of the common components, come join us on this journey, and then you can add whatever special sauce and unique things you have for your infrastructure or your designs into that rack itself. So keep your eyes peeled for the contribution. Come talk to us, come talk to Meta. We want to collaborate on this. We want to make this standard on basically a lot of these high power racks across the board. And you can actually find the URL there. We actually have a blog post. We show a bit more details on kind of why we're doing it, some of the optionality, things we're looking for in the future. So please join the conversation, join us, and we look forward to more collaboration on Mt Diablo. Thanks, everybody.